Let's recap a few important points. The first one is that negative feedback is a system where if our expected output moves away from its ideal value, the system will pull it back to the value it's supposed to be. Say if the stick is supposed to be standing, if it starts falling, there's something which will pull it back, and if it starts falling in this way, there's something which will pull it back and make sure that it stays at the value it's supposed to stay at. What does this mean in terms of op-amps? Is that we expect, like if Vout is supposed to remain at a particular value, when we feed Vout into the negative terminal, after that, if Vout increases, then this value increases and that will pull VO back down. While the other possibility, if VO decreases from its ideal value, this value also decreases and that pushes VO up. So if at all VO moves away from the value it's supposed to be at, the system will pull it back into its original state. Now, since we have such a system in place, we can look at the formula. VO is equal to A times V plus minus V minus. We are assured that VO here is a constant, because we've seen here that if at all VO moves away from its value, it gets pulled back to its original value. So VO will remain a constant. We have assumed A to be an infinity, and so this difference has to be 0, because only when it's multiplied by 0 can it give a constant, otherwise it will give infinity. So only in the case of negative feedback can we be sure that V plus is equal to V minus. We spoke about this in a previous video, and at that time we mentioned that there's a feedback condition in which it works, and that is negative feedback. If at all there isn't negative feedback in the picture, we cannot be guaranteed that VO will remain a constant, and so this argument of V plus minus V minus being 0 doesn't hold. This is true only in the case of negative feedback. The other thing that we need to recollect from a previous video is about the currents going into the op-amp. We saw how the input impedance is infinity, and so the current going into the op-amp will always be 0. These are two important facts to remember to be able to analyze circuits. Remember that this V plus equals V minus is only true for negative feedback circuits. Okay, now let's look at a circuit called the inverting amplifier. Now, as the name suggests, it's an amplifier, so it has to give some kind of a gain. And inverting basically means that the output is going to be in the opposite direction as the input, which means there's going to be a negative sign. Before, what we had done for negative feedback was that we had fed the output directly into the negative terminal. But in this case, we want a gain as well. So we won't feed it directly, we will feed it through a resistor. And then through another resistor, we'll give the input Vn, while the positive terminal will ground it. So let's call this resistor R1 and this resistor R2. Let's analyze, first thing that you need to convince yourself is that it is negative feedback, because if this output increases, the current through the resistor is going to increase, and so this voltage will also increase. Just because there's a resistor, no matter which component is here, this can be any kind of component which does not have a negative sign in its transfer function, and negative feedback will be ensured. So now that we know negative feedback is ensured, we know that V plus has to be equal to V minus. We know that V plus in this case is 0 volts, it's ground. So V minus is also 0 volts. What we also know is that the current going into the op-amp is 0. So whatever current is flowing here, the whole current is going to flow here. So first of all, let's try to figure out the current through resistor R1. The voltage across R1 is Vn minus 0 and the resistance is R1. So using Ohm's law, we get that the current through R1 is Vn upon R1. We know that this exact current, which let's call it I1, this current, whole current I1 is going to flow here through R2. Now, this voltage here, V out, is going to be the voltage across R2 minus 0, because this potential is at 0. And we know that the voltage across a resistor is basically current into the resistance. But in this case, the current is in the opposite direction. So, like this is going to be the positive terminal, this is going to be the negative voltage. So, what we get is that V out is equal to minus V in upon R1 into R2. And that is the transfer function of the inverting amplifier. So we have a negative sign for inverting, and if we make sure that R2 is greater than R1, we get a gain of R2 upon R1. The next circuit that we'll be looking at is called the non-inverting amplifier. So basically, again, we wanted to amplify the input, but in this case we don't want the negative sign in the picture, we want a positive sign. So okay, now even if it's a non-inverting, in the transfer function we want a positive sign and not the negative sign as before. But if we want it to be an amplifier, which means the Vout has to be a constant if the input is constant. If Vn is constant, we expect Vo to also be a constant, and so it is still going to be negative feedback. The feedback does not determine the sign of the transfer function. The feedback determines whether Vout is going to remain constant or not. And in this case, we want Vout to be constant, so we will put the amplifier in negative feedback. So we have our op amp. Like before, we are going to put a resistor to the negative terminal for establishing negative feedback. Before we had we had another resistor here. We had given Vn here and we had grounded this. So, but now since we want the opposite signs, we will ground this and we will give Vn here. Again, let's name these resistors. Let's call them R1 and R2. Let us analyze what happens in the circuit. So, we know that since it's negative feedback, these two voltages have to be equal. We know that this voltage is Vn, so this voltage also has to be Vn. If we know this, we can figure out the current that is flowing through R1. The current through R1 is basically V in minus 0 upon R1, which is Vn upon R1. And we know that the same current has, since the current here is 0, we know that this current has to come from here. The same current is flowing through R2 and bringing it here. So now what we now know is that the voltage across R2 is Vo minus Vn, and that is basically the current into R2, and that is Vn upon R1 into R2, that is Vo minus Vn. We'll rearrange the terms. We get Vo equal to Vn times 1 plus R2 upon R1. And that is the transfer function of a non-inverting amplifier. As you can see, there is no negative sign, there's a positive sign here. And so whatever gain we want, we can choose R2, R1 values accordingly. What is very obvious, since resistances R is always positive, we can see that we cannot get a gain less than 1. So there'll be 1, and we can make R2 very small, or we can also like just short R2 here, so make it 0, but even in that case the gain will be 1. So in this non-inverting amplifier, the gain is always greater than equal to 1. So something that you should notice in both these transfer functions is that there is no A term. It doesn't matter what the A of the op-amp is. By using negative feedback, we have eliminated the point of A. A has to be very large, because otherwise our assumption of VO plus equal to V plus equal to V minus won't hold. But as long as it's very large, its value doesn't matter. And so the problem that we'd spoken about, that getting an accurate A is very difficult, is solved. So you'll notice that in this transfer function, it is VO equals Vin into 1 plus R2 upon R1. And in this case, it is VO equals Vn into R2 upon minus Vn into R2 upon R1. In both the cases, it's only the value of the resistors R1 and R2 which determine the gain, and A does not matter at all.